guys, so today I'm going to go over chapter 7 part 1. I'm going to start kind of in the middle, so make sure you read over the beginning part of the notes. I'm going to start on this slide. It talks about the octet rule. So the octet rule says that chemical compounds tend to form so that each atom, by gaining, losing, or sharing electrons, sharing is what we're going to focus on, has an octet of electrons in its highest occupied energy level. And an octet of an electrons is basically a noble gas configuration. And so here, the noble gases are right here. And you can see how they all have a full S and a full P orbital. And so they all have 8 electrons in their valence shell or their outer shell. So neon has 8, argon, all of these have 8. It's down when we get to krypton, so they do have these d orbitals, but remember that d orbitals are 1 less. And so this would be 3d, 4s, and then 4p. And so it's still 8 electrons in their valence shell or their outer shell. The one exception is helium. Because it's the first energy level, there are only 2 electrons. It only has 1 s2 for its valence shell. And so everything wants to have 8 except for here, the first row, hydrogen and helium, their stable configuration is 2 electrons. And so the exception is hydrogen wants a duet to be like helium. So hydrogen's going to try to get an extra electron to be like helium. It doesn't need 8. It only wants to fill that 1 s orbital. Everything else wants to be like a noble gas and have 8 electrons. So here you can see valence electrons are the outer shell electrons. So group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13, or on your periodic table, it's called 3A because they omit transition metals, has 3, 4, 5, 6, 7, 8. And so you're just going by group number of these main group elements. And so this is different from the ionic compounds where you're talking about charges, how much they would lose. It's the same concept, but here we're sharing to get to 8 instead of losing or gaining electrons as in an ionic compound. So these are covalent bonds where elements are sharing electrons so that they get to 8. And most of what we're dealing with here are these non-metals to the right of this stair step right here. Trying to get to a noble gas configuration, hydrogen and all the other nonmetals. And so here are the valence electrons. They're going to be the same as their S and P electrons in the highest level, and it's going to be the same as the group number. Either if it's 13, you just take the 3, or in our periodic table, go by that number right there. And so for covalent bonding, these elements are going to share electrons. So instead of one stealing another one, like in an ionic bond, or one giving away another one, they're going to share. And so for fluorine, each fluorine wants an extra electron in order to be like neon, have 8 electrons. And so what it's going to do is these orbitals here are going to overlap and share so they each feel like they have those 2 electrons. So they're going to share their electrons to try to attain an octet of electrons. Each one has 7 in its valence shell, the highest shell. It wants 8, so it'll share electrons. So the way we represent molecules is by something called Lewis structures. And all we're doing here is we're using electron dot notation to represent valence electrons. So the valence electrons, these are the outer shell electrons. And we're going to use dots to represent it. And then we're going to use dots in the center of the 2 elements to represent bonds. where 2 electrons represent a chemical bond. And so Lewis structures, the way these work is that we've got these shared or bonding electrons. These electrons will always be in groups of 2. And so groups of 2. There are cases where there's 1, but those are called free radicals. They're very reactive because they really want to be in groups of 2. So we've got the shared or the bonding electrons that are in between 2 elements or 2 atoms. And then we've got our unshared or lone pair electrons that belong exclusively to 1 atom. So here, this. So this is ammonia. It has 3 chemical bonds to hydrogen. These electrons are shared. This is its unshared or lone pair of electrons. So these are different kinds of electrons, shared and unshared. And so here, this is a system that I like to use for drawing Lewis structures. You can use whatever system you want. I've done it many ways. This is the easiest one to explain, and it's the one that will always give you the right answer. If you do this correctly, you will get the right answer. So we're going to go over this with several different compounds, and then hopefully you'll get the hang of it after we do it several times. And so what we want to do is draw this Lewis structure Br2. And so what this means is that the 2 bromines are bonded together. We want to know where their electrons go. So the first thing we want to figure out is how many electrons are needed here. We've got 2 bromines. Each one needs or wants 8 electrons. The octet rule, everything wants 8. So we've got 2 atoms that need 8 electrons. That's 16 needed electrons. The next one we want to see is how many are available. So that's from the valence shell. 2 bromines. Bromines is in group 7. And so each bromine has 7 electrons to share. So we've got 2 bromines. Each has 7. That's 14 electrons that are available. Needs 16, has 14. And so shared electrons are going to be the difference between those. That's 2. Unshared will be whatever is left. 14 minus 2 equals 12. So I'm going to take these 2 shared electrons, put them in between the 2 bromines. Then I'm going to add these 12 so that everyone has its full octet. So here, each bromine feels like it has 2, and so it needs 6 more. So I'll put 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Like that. Now, you've taken care of all the electrons that bromine has. Each has 7. It's sharing right here so that each of it feels like it has 8 electrons. Next, let's try this with ammonia. Here, the first element listed, unless it is hydrogen, you're going to put that in the center. And so sometimes hydrogen will be first for an acid, like, for example, HCl. In that case, chlorine's set in the center because hydrogen is never a central atom. But usually, unless it's hydrogen, you put the first one in the center. And then I'm going to surround it with the hydrogen. So hydrogen, hydrogen, hydrogen. So we've got these 4 atoms. We want to figure out what is needed. So we've got 1 nitrogen that needs 8. Nitrogen needs 8, but hydrogen, so nitrogen wants to be like neon. Hydrogen just wants to be like helium and needs 2. So we've got 1 nitrogen that needs 8, 3 hydrogens that need 2. And so 8 plus 6 is 14. That's how many are needed. Available, we've got nitrogen in group 5, hydrogen in group 1. And so we've got 1 nitrogen that has 5, 3 hydrogens that have 1. And so what we have available is 8 electrons. So this is what we need. This is what we actually have. To take care of the octet rule, we're going to share the difference between these. And so the difference between that would be 6. And then whatever is left over is unshared. And so we've got 6 and 2. This is going to go in between, so we're going to put 2 there, 2 there, and 2 there. That takes care of our 6. There's 2 unshared. Each hydrogen is happy because it has 2 electrons. And so we're going to add the 2 here because nitrogen needs 2 more. So 2, 4, 6, 8. There, we have taken care of everything. Let's keep going. Here, draw the Lewis structure for CH3I. And so I'm going to put carbon in the center. I'm going to surround it with whatever's left. H, 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 I. Doesn't matter where you put that. You could put the I anywhere else. Just surround it by these 4. So we're going to see what's needed. So we've got 1 carbon and 1 iodine. Each of them need 8 because everything needs 8 except for hydrogen, which needs 2. So we've got 2 that need 8, and we've got 3 hydrogens that need 2. So we've got 16 plus 6, so that is 22. Available carbon is in group 4A, so it has 4. Iodine's in group 7. It has 7. Hydrogen has 1. And so we've got 1 carbon that has 4. We've got 1 iodine that has 7. We've got 3 hydrogens that have 1. So that's 7 plus 3, 10, 14. I'm going to take the difference. That has to be shared. 22 minus 14 equals 8. The difference will be unshared. 6. So 8 must be shared. 6 is unshared. So you might be thinking that all you're doing here is just putting 2 in between the elements, so why do we need to go through this? Well, sometimes it's not always just going to be 2 in between, and that's where it's going to be more helpful to use this system. So I have 8 electrons there, 4 bonds. Each hydrogen's happy, it has 2. Carbon is happy, it has 8. Iodine needs 6 more, so that's where those 6 unshared will go. 2, 4, 6. Taking care of that and that. Okay, so double bonds are when you have 2 pairs of electrons between atoms. And then triple bonds are when you have 3. So that's as high as it can go. It either can be a single bond, a double bond, or a triple bond where you have 3 pairs of electrons. And that's where this system is going to be really helpful, is figuring out when you need a double or triple bond. So in this example, we've got CH2O. Let's put carbon in the center. Then let's put our oxygen here. We can put our hydrogen here and our hydrogen here. Doesn't really matter as long as you put carbon in the center. Now we're going to use this method. We want to figure out how many are needed. So we've got carbon and hydrogen, or oxygen. They need 8. We've got 2 that need 8, and then we've got 2 hydrogens that need 2. This one's always going to be 2 or 8. The only one that gets 2 is hydrogen, but hydrogen is very common, so we see it often. 16 plus 4 is 20. That's how many are needed. What we have is 1 carbon that has 4 from its valence shell, because carbon is in group 4, oxygen's in group 6. And so then we've got 1 oxygen that has 6, and we've got 2 hydrogens that have 1. So 4 plus 6 is 10 plus 2 is 12. The shared will then be 20 minus 12, which is 8. The rest will be unshared. Shared, unshared. So we're going to start by putting 2 in each spot. However, now we've only used up 6, so we have another 2 electrons that have to be shared. Each hydrogen's happy. Hydrogen can never have a double bond because it only wants 2. And so that other 2 is going to have to go right here. That's taken care of our 8 shared. Now we have 4 unshared. So we look at hydrogen. Each of those are happy. Carbon has 2, 4, 6, 8. Anything that's shared, each one feels like it has it. So carbon's happy. Oxygen has 2, 4. It needs 4 more. So we're going to put a lone pair here and a lone pair there. And so you can also draw this with bonds that look like this, and then show that there are 2 lone pair right there. So we've taken care of shared and unshared. CO2, carbon in the center. We're going to put an oxygen on each side. We've got 3 atoms here that need 8. No hydrogens. So 3, 1 carbon, 2 oxygens. They all need 8. 24. We've got 1 carbon that has 4 from its valence shell. 2 oxygens that have 6. So that's 12, 16. Shared, 24 minus 16 equals 8. And then 16 minus 8 is 8. So we're going to share 8, have 8 unshared. So we're going to put some here and here. And we've got 4 more. So you actually could put a single and a triple bond, and that would be what's called a resonance structure of CO2. The better option here, I would not take off if you did that. The better option is to put, just to even this out, because each one can have a double bond. If there's a hydrogen here, then you obviously would only have a single bond. But we're going to put all 8 electrons, have 2 double bonds, so that takes care of our shared. Unshared is 8. And so we're going to, this carbon is happy. It has 8. 2, 4, 6, 8. Each oxygen, though, needs 2 more. So we're going to put 2, 4, 6, 8. And so this looks like this, where you have oxygen with 2 lone pairs. You can go through and count and make sure everybody has its octet satisfied, which it does. Next one, we have HCN. And so hydrogen's not going to be in the center because that just means this is an acid. Hydrogen will never be in the center. So we're going to put carbon in the center and then like that. Needed, we've got 1 hydrogen that needs 2 and then 2 that need 8. So it's 18 like that. Available, we have 1 hydrogen that needs or has 1 available. We've got 1 carbon that has 4 available. 1 nitrogen that has 5 available. 5 plus 4, here we've got 10. So shared will be 18 minus 10 equals 8. And then unshared will be 10 minus 8 equals 2. So we've got 8 shared, 2 unshared. So we'll put 2 right there, 2 right there. That only gives us 4. Hydrogen can never have anything more than a single bond. So that means the rest of these have to go between carbon and nitrogen. So I'm going to put 2 more and 2 more, giving it a triple bond. That takes up all of our 8. Hydrogen is now happy, it has 2. Carbon's happy, it has 2, 4, 6, 8. Nitrogen has 2, 4, 6. needs 2 more. That takes care of our unshared. You can also draw this like this. Like that. Okay, next we're going to look at our polyatomic ions. Everything's going to be exactly the same, except this carries a charge. And so you're going to be subtracting or adding electrons based on the charge, because you've got this covalently bonded compound, but it's an ion because it's carrying a charge. And so if you have a positive charge on the polyatomic ion, which only happens really with ammonium, you're going to subtract from the available electrons. And so here we've got NH4, so N, H, H, H. It's a positive charge right there. We want to draw the Lewis structure from that. The needed will be the same. We've got 1 nitrogen that needs 8. We've got 4 hydrogens that need 2. So 8 plus 8 is 16. Available, 1 nitrogen has 5. 4 hydrogens have 1. So that's 9. And so here you know you have to do something because you have an odd number of electrons, and that's not going to work. And so if you forget to do that, this will remind you. The positive, you just need to remember that the positive, it's the opposite of what you would think. The positive means you take away an electron because you have an extra proton. You're missing an electron. So minus 1. This is the thing here that we need to do. So you actually only have 8 because of that positive charge. Now 16 minus 8, equals 8. 8 minus 8 equals 0. So everything is shared. 2 here, 2 here, 2 here, and 2 here. And then we make sure you put it in brackets and add the positive charge right there. Now, if you have a negative charge, you add to the available electrons. So here, nitrate, we've got NOOO. It's a negative charge. And so we've got 4 atoms that need 8. 32. 1 nitrogen that has 5 available. 3 oxygens that have 6 available. So 18 plus 5, 23. But you have this negative charge, add 1 electron, gives you 24. 32 minus 24 equals 8. 24 minus 8 equals 16. And so we've got 8 shared electrons. I'm going to put 2 here, 2 here, 2 here. You have 2 more. And so either one, they're all oxygen, so you can just pick one. Put it right there. One of them is going to be a double bond. And then the unshared electrons will go to complete the octet. Nitrogen's happy. This oxygen has 4, so it only needs 4 more. This oxygen needs 6 more. This oxygen needs 6 more. So that should give us 6, 12, plus 4 is 16. Taking care of unshared and shared. And so this looks like this. Like that. And then brackets like that. Octet exceptions, we're not going to do any examples of this. I just want you to know about them. So this could be a multiple choice question on a quiz. Boron tends to form bonds to achieve 6 electrons rather than 8. And so it has things like this, BH3, BF3, where it only has 6 electrons around it. And then phosphorus and sulfur can have up to 10 to 12 electrons due to the d orbitals. When you do compounds, assume it has 8. I don't want this to mess up your practice with the octet rule. I just want you to know that it is possible. This is what happens in the real world, is that phosphorus can have up to 10 and sulfur can have up to 10 to 12 electrons. But when you are doing your problems, assume that it is not one of these exceptions. I just want you to know that they exist. You will not have any practice problems on them. Okay, so that is the end of this chapter. Go over the worksheet. Email me if you have any questions. And hopefully you can get the hang of it with some practice.